Hi, my name is Kat and I'm a librarian here at North Vancouver City Library, and this week's Summer Reading Club theme is The Great Unknown. And for our STEAM Saturday Science experiment, we are going to explore what was once a true mystery: black holes. The ominously named black hole describes what we see, or rather what we don't see. Black holes are space objects that exert so much gravity that nothing can escape them, not even light. This was once a true mystery, only really known through some fancy physics formulas that identified the possibility of these entities existing, but no way to really prove that they did. So, in order to examine this idea, we need to talk about gravity. Gravity is a force that is exerted between two objects, and it is affected by two things: the size of the objects and the proximity, or how close those two objects are to each other. So you standing on the Earth are very, very close to it, and therefore cannot escape the Earth's gravitational pull without some very fancy rockets. Give it a try, jump up and down, and feel the force of gravity pulling you back in. Likewise, the moon, which rests just in orbit with us, is far enough away that it doesn't get pulled in any closer, even though it's bigger than we are. So, knowing this, we would expect black holes to be enormous, but they're not. They're really, really small. And this is because their matter is very densely packed. We now know that black holes are created when stars run out of fuel and collapse in on themselves. The star compacts and compacts and compacts until what is left of it is so densely packed it reaches what is known as infinite density. There is no space left between its smallest molecules, and it reaches this point where it becomes a singularity, the center of a black hole. It pulls everything into it, including light, and nothing can escape. So let's try a science experiment to see what that pull of gravity would be like. For this experiment, you're going to need a blanket or some other piece of fabric. It's best to use something that has a lot of stretch, so something that is elastic or spandex, just so it has a bunch of give to it. And then you're also going to need a few different kinds of balls. So baseballs, some bouncy balls, marbles will even work, but different sizes and different weights. The other thing that you will need is a partner or two. This experiment does not work if you don't have at least two people to hold the blanket tight. You and your partner are going to give the blanket a nice big pull, so stretching it from side to side. If you're having a hard time controlling things during this experiment, I recommend that you fold the blanket down to make it a little bit smaller. This makes it easier to manage the objects moving through your space-time, which is what this blanket represents, our space-time. So it represents two-dimensional space-time, so forward and backward space and left and right. Whereas real space-time consists of three dimensions: up, down, left, right, forward, and backwards, as well as time. But for our experiment, we only need to see it in two dimensions. So we're going to grab a ball, which is going to represent an object in our space-time. So this could be a planet, it could be an asteroid, or it could be light or a photon. So we stretch out the blanket, we drop on the ball, and we're just going to tilt the blanket back and forth to see how objects would regularly move through our space-time. And as we can see, they just sort of move in these nice straight lines unless we start doing weird things with our space-time. So that's good to know. They will generally move in straight lines. Now let's try a larger object to just see what it does to space-time just by being in it. Give the blanket a nice big stretch, and we drop in the ball. And as you see, the ball is pushing down on the blanket. It's creating a crater in the blanket. And no matter how much we pull, the blanket is still going to have this crater, this divot in it from the ball. And this is what actually happens to space-time when objects with mass exist in them. The space-time warps around those objects according to their gravitational field. And what this means is that anything that tries to move through the space-time past this object can be caught in its gravitational pull. So let's just give that a try. Have a little ball, and we're going to try to roll it past, and it just gets pulled in because the blanket is curved down towards the ball, which is exactly what gravity would do. So let's switch it out. This baseball is actually pretty light, so I'm going to switch it for a heavier ball, which is this rubber ball. So while it's smaller, it's more densely packed and therefore is heavier, has more mass. It will create a bigger pull in the blanket, kind of like our black hole. Give it a pull, and same thing. It almost has the same dip as the baseball, even though it's much smaller. So we can put our other ball on and try to roll it past, and same thing. It gets caught in the pull and just comes straight in. So this is a good time to talk about the three parts of a black hole. A black hole is made up of a singularity, which is the infinite density packed object at the center of the black hole that has so much gravity that nothing can escape it. Outside of that, you have an inner event horizon, which is a line that once anything crosses it, including light, will get trapped in the gravitational pull and never be able to escape. It just gets pulled into the black hole. Outside of that, you have an outer event horizon where objects can safely view or exist around the black hole without getting pulled into it. So you can experiment with your ball to see if you can get or figure out where these different parts of your black hole exist. So where is the inner event horizon and where is the outer event horizon? So can we get this ball to go around? Nope, it got caught in the inner event horizon. But play with it. See if you can get one of your smaller balls to roll across the blanket without getting caught in the gravitational force of the larger ball. Give this experiment a try. Have fun thinking about these wonderful, mysterious objects in space, and we'll see you next time.